A 40-ton machine slams into hardpan soil at 15 miles per hour. The frame doesn't flex, the bowl doesn't crack, the engine doesn't miss a beat. This is the Caterpillar 637D, and it's been doing this exact job for 40 years straight. Original hydraulic seals, original transmission, zero structural fatigue. They literally don't make them like this anymore. Welcome to the golden age of scraper construction, when manufacturers built machines designed to outlast the companies that made them. Number 10. Terex TS24. Let's start with a machine that embodied the American approach to heavy equipment. If the specs say it needs to be strong, make it twice as strong just to be sure. The Terex TS24 featured a bowl capacity of 24 cubic yards, but calling it a 24-yard scraper undersells what this machine really was. Terex engineers designed it to consistently carry 28 to 30 yards in real-world conditions. The extra capacity came from sophisticated bowl geometry and a tailgate design that could compact material during loading. The frame construction used 1-inch thick high-tensile steel plate in critical stress areas. Most scrapers used half-inch plate. Terex's engineers ran finite element analysis, cutting edge for the early 1980s, and identified every stress concentration point, then doubled the material thickness in those areas. The result was a frame that could handle shock loads that would destroy competitors' machines. The cutting-edge assembly used a bolt-on system with 12 attachment points instead of the standard 8. This distributed wear more evenly and made edge replacement faster. The edges themselves were made from a proprietary steel alloy that Terex developed in-house, containing higher manganese and chromium content than standard scraper blades. These edges lasted 40% longer than conventional ones. The hydraulic system operated at 3,500 psi, when most scrapers ran at 2,500 psi. This wasn't for speed, it was for power and precision. The higher pressure allowed smaller cylinders to generate the same force, reducing weight while improving response. Terex also used double-acting cylinders with cushioned end caps that absorbed shock loads, protecting the system from the violent impacts inherent in scraper work. The ejector system was chain-driven rather than hydraulic. While this might seem old-fashioned, chains provided positive mechanical advantage that couldn't fade or slip under heavy loads. The chains were aircraft-grade alloy steel, rated for 3 times the maximum ejection force. They outlasted the machines. Number 9. Caterpillar 631E. Caterpillar's response to the earth-moving boom of the 1980s was a scraper that redefined what heavy-duty meant in the industry. The 631E used a revolutionary cushioned hitch design that isolated the tractor from the scraper bowl during loading. Traditional rigid hitches transmitted every impact directly into the tractor frame, causing fatigue and eventual failure. Caterpillar's engineers developed a hydraulic cushion system with accumulators that absorbed shock loads up to 50,000 pounds of instantaneous force. This single innovation extended tractor frame life by an estimated 50%. The bowl was constructed from Hancock's 400 steel plate, a Swedish material with 400 Brinell hardness that was extremely expensive but virtually wear-proof. The floor of the bowl alone could handle 10,000 loading cycles before requiring replacement. Standard scraper bowls needed replacement after 3,000 to 4,000 cycles. The cutting edge was a straight blade design, but the mounting system was ingenious. Caterpillar developed a quick-change edge system using tapered pins that locked under load. 2 operators could change all cutting edges in under 30 minutes without welding or specialized tools. This minimized downtime and kept the machine productive. The power plant was a 3408 diesel producing 450 horsepower, but the real story was the cooling system. Caterpillar used a modular cooling package with separate cores for engine coolant, transmission oil, hydraulic oil, and charge air. Each system could be removed and cleaned independently. The entire cooling package was mounted on vibration isolators and could swing out for service access. This attention to maintenance access reflected Caterpillar's understanding that uptime was everything in earth-moving. The transmission was a planetary power shift design with 7 forward speeds. The gear ratios were specifically calculated for scraper work, providing maximum rim pull in first gear for loading, optimal speed for hauling in 4th and 5th, and an overdrive 6th gear for light loads and return trips. The 7th gear was an emergency limp-home ratio that allowed the machine to operate even with transmission damage. Over 4,000 units were produced, and survival rates are remarkable. Operators report machines with 30,000 hours still running original engines and transmissions, a testament to the over-engineered construction. Number 8. International Harvester 295. Before International Harvester imploded in the agricultural crisis of the mid-1980s, they built one of the most innovative scrapers of the decade. The IH295 pioneered the use of aluminum in scraper bowl construction. This sounds counterintuitive. Aluminum is softer than steel, but IH's metallurgists developed a specific aluminum alloy with copper and zinc that provided exceptional strength-to-weight ratio. The aluminum bowl was 30% lighter than steel, reducing overall machine weight and improving fuel efficiency. But the real advantage was corrosion resistance. These bowls didn't rust. The floor of the bowl used a sacrificial wear liner system. Replaceable aluminum plates bolted to the bowl floor took the abuse, while the structural bowl remained protected. The plates were cheap to manufacture and easy to replace, extending bowl life indefinitely. I developed an electronic load monitoring system, extraordinarily advanced for night. Sensors measured bowl weight in real time and displayed the information to the operator. This allowed precise loading to maximum capacity without guesswork. The system used strain gauges mounted on the bowl support arms, feeding data to a digital display. This was before digital dashboards were common even in cars. The steering system used full hydraulic power assist with no mechanical linkage backup. This worried some operators initially, but the system had triple redundancy, 2 independent pumps and an accumulator that stored pressure for emergency steering if both pumps failed. The result was effortless steering control that reduced operator fatigue dramatically. The ejector system used hydraulic cylinders but with an innovative pressure sequencing valve that prevented hydraulic shock. As the ejector pushed material, pressure would spike when encountering compacted or sticky material. IH's valve system bled off pressure spikes, protecting the cylinders and seals from damage. This single innovation extended seal life from 2,000 hours to over 8,000 hours. When IH collapsed, scraper production ended abruptly. Fewer than 600 units were built, making the 295 one of the rarest quality scrapers. Parts are nearly impossible to find, yet dedicated owners keep them running through fabrication and adaptation. Number 7. Caterpillar 657E. The largest scraper Caterpillar ever produced was a monument to the philosophy that there's no replacement for displacement. With a 44 cubic yard bowl capacity, the 657E wasn't just big, it was engineered with massive proportions in every system. The frame rails were 12-inch steel I-beams, the same section used in building construction for medium-rise structures. The crossmembers were 8-inch channel steel. The entire frame could support the machine's 180,000-pound operating weight with a safety factor of 4, meaning it could theoretically handle 720,000 pounds before structural failure. The bowl cutting width was 12 feet, and the cutting edge alone weighed 3,200 pounds. The edge was segmented into 6 sections, each replaceable independently. The segments interlocked with tapered joints that became tighter under load, preventing separation even when one section was completely worn. 2 3412 diesel engines provided 800 combined horsepower, but they were mounted tandemly, one in the tractor, one in the scraper unit. This distributed power reduced driveline stress. The rear engine could be declutched during light loads or return trips, saving fuel. Both engines shared a common cooling system with a radiator package the size of a compact car. The hitch system used a load equalizing design that automatically distributed weight between tractor and scraper axles based on bowl load. Sensors measured tongue weight and adjusted hydraulic cylinders to maintain optimal weight distribution. This improved traction during loading and stability during hauling. The suspension system used nitrogen-charged accumulators at each wheel station, providing 14 inches of travel. This allowed the 657E to maintain speed over rough terrain that would force smaller scrapers to slow down. The suspension also protected the frame from shock loads, contributing to the machine's legendary durability. Only 267 units were built before emissions regulations and changing economics killed the market for such large scrapers. Today, they're prized by massive earth-moving operations and mining companies who appreciate their ability to move material at lower cost per yard than any modern alternative. Number 6. John Deere. The 8062 Deere's entry into the large scraper market brought agricultural equipment reliability standards to heavy construction. The 8062 featured a 32 cubic yard bowl with what Deere called their Dura-Bowl construction. The bowl was fabricated from overlapping plates with welded joints ground flush and then heat-treated. This process created a bowl with no stress risers or weak points. The heat treatment also work-hardened the steel, effectively increasing its hardness by 60 Brinell points without making it brittle. Deere pioneered the use of bolt-on wear plates in strategic high-wear areas. Previous scrapers required welding new steel when wear occurred, which introduced heat stress into the structure. Deere's bolt-on plates could be replaced in the field without welding equipment, and the plates themselves were made from AR400 abrasion-resistant steel that outlasted the surrounding structure. The hydraulic system used a closed-center design with load sensing, meaning the pump only produced flow when a function was activated. This reduced parasitic power losses and improved fuel efficiency by approximately 15% compared to open-center systems. The system used a single variable displacement pump rather than multiple fixed displacement pumps, simplifying maintenance. The cutting-edge assembly featured automatic blade pitch adjustment. Hydraulic cylinders could alter the blade angle during loading to optimize cutting depth and reduce draft force. Operators could preset blade pitch for different soil conditions, and the system maintained that pitch automatically regardless of terrain variations. The operator's station was the most advanced of any scraper in the 1980s. Full climate control, air suspension seat, fingertip hydraulic controls, and a diesel-fired cab heater that could operate independently of the engine. Deere understood that operator comfort directly impacted productivity and reduced labor turnover. The transmission was a power shift design with automatic shift logic that could be overridden manually. The automatic mode used algorithms that considered engine load, ground speed, and operator throttle position to select optimal gears. This reduced fuel consumption and prevented operators from lugging the engine or over-revving it. Approximately 1,100 units were produced before Deere exited the scraper market to focus on other equipment lines. Surviving examples are valued for their reliability and ease of maintenance. Number 5. Allis-Chalmers. The AC460. Before financial troubles forced Allis-Chalmers out of the construction equipment business, they produced a scraper that operators considered the most comfortable machine in the industry. The AC460 featured the first fully suspended operator's platform in a scraper. The entire cab was mounted on 6 isolators that filtered out 95% of vibration and shock. Working a 460 for 12 hours produced less operator fatigue than 6 hours in most competitors' machines. The bowl design used a compound curve that Allis-Chalmers developed using early computer modeling. The curved floor and sides reduced material adhesion in sticky soils and improved ejection efficiency. The bowl could discharge its entire load in 8 seconds, half the time of conventional scrapers, reducing cycle times. Allis-Chalmers used a unique hydraulic system with 2 independent circuits, one for steering and critical functions, one for implement controls. If the implement circuit failed, the machine remained fully controllable. If the steering circuit failed, a mechanical bypass allowed limited steering capability. This redundancy was unusual in the era. The cutting edge was a curved design rather than straight. The curve matched the bowl's entry geometry, reducing cutting forces by approximately 20%. This allowed deeper cuts with less power, improving productivity. The curved edge was more expensive to manufacture and replace, but the performance advantages justified the cost. The tires were custom designed by Goodyear specifically for the force. The tread pattern and carcass construction provided optimal traction in soft soil while minimizing rolling resistance on hard surfaces. The tires were rated for 100,000 miles, double the standard scraper tire life. The engine was a turbocharged and aftercooled 6-cylinder producing 425 horsepower. The aftercooling system used a separate charge air cooler that reduced intake air temperature by 150 degrees Fahrenheit. significantly improving power density and reducing engine stress. When Allis-Chalmers sold their construction division in 1983, the 4060 was discontinued despite strong sales. Only about 400 were produced, making them highly collectible today. Number 4. Euclid S40. Euclid, the company that literally invented the modern scraper, produced their finest machine in the 1980s. The S40 was a 40 cubic yard machine with one defining characteristic: indestructibility. The frame was over-engineered to a degree that seemed excessive until you watched one work. Euclid used a box section frame rather than I-beams, providing superior torsional rigidity. The frame could twist 12 degrees without permanent deformation, critical for rough terrain work. The bowl was fabricated from half-inch plate steel throughout, no thinner sections anywhere. Most scrapers used 3/8-inch plate on the sides and upper sections. Euclid's engineers calculated that using uniform thickness simplified welding, reduced stress concentrations, and only added 2,400 pounds to machine weight, a worthwhile trade-off for extended service life. The cutting-edge mounting system used 24 bolts instead of the typical 12 to 16. Each bolt was a 1.25-inch diameter grade 8 fastener. The massive number of attachment points distributed stress so evenly that edge mounting brackets rarely cracked, a common failure point on other machines. Euclid pioneered the use of planetary final drives at each wheel station. These drives provided a 5-1 gear reduction at the wheel, allowing the main transmission to operate at lower torque levels. This extended transmission life and improved efficiency. The planetary drives were sealed units filled with gear oil and designed to last the machine's lifetime without service. The ejector system used 4 hydraulic cylinders rather than the typical 2. This provided redundancy. The ejector could still function with 1 or even 2 cylinders disabled. The extra cylinders also reduced individual cylinder stroke length, improving reliability and reducing maintenance. The operator's controls used a unique joystick system that Euclid developed in-house. One joystick controlled steering and throttle, another controlled all hydraulic functions. The system reduced hand and arm movement, significantly cutting operator fatigue. The learning curve was steep, but experienced operators were notably more productive. Approximately 900 S40s were built before the scraper market collapsed. They're considered by many operators to be the finest scraper ever produced, and working examples sell for premium prices. Number 3. Caterpillar 633E. Caterpillar's mid-range scraper became the industry standard against which all others were measured. The 633E featured a 33 cubic yard bowl with what Caterpillar called their integrated bowl and apron design. Traditional scrapers used a separate apron that opened and closed to control material flow. The 633E's apron was an integral part of the bowl structure, eliminating the joints and hinges that typically wore and failed. The integrated design also improved bowl strength and reduced maintenance. The cutting edge used Caterpillar's patented Advancis carbide insert system. Small carbide tiles were brazed into pockets in the steel edge, creating an edge that was 90% steel, 10% carbide. This combined the toughness of steel with the wear resistance of carbide. Edge life increased by 300% compared to conventional steel edges. The cushioned hitch system used dual nitrogen accumulators with a total capacity of 2 gallons. When the blade hit an obstruction, the accumulators absorbed the shock, then returned the energy to help drive the blade into the ground. This energy recovery system actually improved cutting performance while protecting the frame. The 348 diesel engine used Caterpillar's ADEM, Advanced Diesel Engine Management, electronic control system, one of the first production applications of electronic engine management in heavy equipment. ADEM optimized fuel delivery, controlled turbocharger boost, and provided diagnostic capabilities years ahead of competitors. The cooling system used a hydraulically driven reversible fan. The fan could be reversed to blow debris out of the radiator rather than drawing it in. This kept the cooling system clean and maintained efficiency. An automatic reversing cycle ran every 30 minutes during operation, preventing debris accumulation. The transmission offered push-button shifting, unusual for scrapers in this era. Operators could pre-select gears and the transmission would shift automatically when conditions allowed. This reduced drivetrain shock and improved component life. Over 600 to 500 units were produced, making the 633E the most common large scraper of the 90s. The combination of durability and parts availability keeps many examples working today. Number 2. Hancock 6030. A relatively unknown manufacturer produced one of the most innovative scrapers of the decade. Hancock Engineering was a small company that built specialized equipment for the mining industry. Their 6030 scraper incorporated mining equipment technology that was far ahead of mainstream construction equipment. The frame used ultra-high-strength steel with yield strength of 130,000 psi, nearly double that of conventional structural steel. This exotic material allowed Hancock to build a frame that was lighter yet stronger than competitors' frames. The weight savings improved fuel efficiency and reduced tire wear. The bowl featured a completely smooth interior. No rivets, bolts, or welds protruding into the bowl space. Hancock used a special welding process where welds were ground flush and then covered with a wear-resistant coating. Material flowed through the bowl without catching on protrusions, improving loading efficiency and ejection performance. The hydraulic system operated at 5,000 psi, the highest pressure of any scraper produced. This required special components and seals, but the performance advantages were substantial. Cycle times were reduced by 20% compared to conventional machines. Hancock developed an automatic grade control system that used a laser receiver mounted on the scraper. The system could automatically maintain cutting depth to follow a laser plane, allowing precise grade control without constant operator input. This technology wouldn't become common in scrapers for another 20 years. The ejector used a rack and pinion drive system rather than chains or hydraulics. Electric motors drove pinion gears that engaged racks mounted to the ejector panel. This provided precise control and eliminated the maintenance associated with chains and hydraulic cylinders. Only about 150 units were produced before Hancock was acquired by a larger company that discontinued scraper production. The few surviving examples are technological curiosities that demonstrate how advanced scraper design could have been. Number 1. Caterpillar 651E. The pinnacle of 1980s scraper engineering was a machine that Caterpillar built specifically for the mega projects of the era. The 651E was an open bowl scraper with 51 cubic yard capacity, the largest open bowl scraper ever mass-produced. Open bowl design meant no apron or ejector. The machine loaded with the bowl open and spread material by dumping while moving forward. This simplified design eliminated the weight and complexity of ejector systems. The frame was a masterpiece of structural engineering. Twin I-beam rails ran the entire length with cross members every 30 inches. The frame could support 220,000 pounds, nearly double the machine's typical operating weight. This massive overbuilt structure meant the frame was effectively unstressable under normal operating conditions. The bowl was constructed from 5 8-inch hardox plate throughout. The floor alone weighed 8,400 pounds. The cutting edge was 6 feet wide at the center, tapering to 4 feet at the wings. The center section used replaceable carbide inserts for extended life in abrasive materials. 4 3412 diesel engines, 2 in the tractor, 2 in the scraper unit, provided 1,600 combined horsepower. The engines were synchronized electronically to share load evenly. Any engine could be shut down independently, allowing the machine to operate with reduced power if one engine failed. The hitch system used a combination of mechanical and hydraulic components that could transfer up to 300,000 pounds of push-pull force between tractor and scraper. This massive capacity allowed push loading with tandem tractors, cutting cycle times in half. The suspension used 6-foot diameter tires with custom treads developed by Michelin. The tires alone cost $15,000 each in 1980s dollars. They were rated for 40,000 miles, but commonly exceeded 80,000 miles in service. The operator's station included innovations like automatic climate control, a refrigerator, and an AM/FM CB radio. Unheard of luxuries in scrapers. Caterpillar understood that operators working 12-hour shifts in remote locations needed every comfort available. Only 89 units were produced. The 651E was simply too large and specialized for most projects. The machines that were built went to massive earth-moving projects, dam construction, open-pit mining, and military base construction. Today, surviving examples are museum pieces or still working on the largest earth-moving projects in the world. So that's it for today. If you like this video, then please hit the like and subscribe button for more videos. Thanks for watching.